So as we go through today's topic in 8.8, we're just trying to find the volumes of these with cross sections with two types of triangles, equilateral triangles and isosceles right triangles, and then also a semicircle. Biggest thing is trying to make sure you remember some of the formulas. Now, I'll be honest with you, I don't know off the top of my head what the area of a equilateral triangle is. They're going to give you that formula, okay? We should know by heart how to find the area of a semicircle. We should know by heart how to find the area of a isosceles right triangle. Those are the things they're expecting us to know. The equilateral triangle, they're not. So they're going to give us that formula when we come to it here in a moment. So that helps with some of what we're doing. So again, as we talked about yesterday, the volume of a solid with known cross sections is equal to the integral from A to B of the area of the cross section dx. And then again, in this case, we have it perpendicular to the x-axis is what we're focused on right now. But as you look at the homework problems, as you look at the note problems, they're going to switch between what are you perpendicular to. So even though we're doing most of the stuff in the lesson right now with respect to the x-axis, perpendicular to the x-axis is the same stuff with perpendicular to y. Just make sure you converge your equations over is what you got to make sure you do. So when we're working with the cross section being an equilateral triangle, here is the formula. It is the square root of 3 over 4 times the side length squared dx, where the side length is our f of x minus g of x. So top minus bottom or right minus left, depending if we're doing it in terms of y. Isosceles triangle formula. Now here's the challenge, and I guess we could have done the cross sections like we did yesterday with those extra pictures. The hypotenuse is not the distance between the two on the isosceles right triangle. It's not the distance between the two curves. Okay, it's actually one of the legs, which makes it a lot nicer to work with. So with that in mind, all right, we're going to go the integral from A to B of basically 1/2 side squared, and then dx. Again, if I was looking at my curve, so if I try to draw the curve from yesterday, the fishy curve, we would have there, and then I'd try to come up that's not three-dimensional. Let's go right angle back down. There we go. So there is my right triangle. So the hypotenuse is actually out in space coming down, where we came up vertically from one of the bottom curve, came up straight up in a right angle, and then the bottom leg went from curve to curve. And then once we hit the max for whatever the height of that triangle was, then we went diagonally down to the other side. So this is the side length. So where S is equal to, again, f of x minus g of x. Again, there's some applets out there, GeoGebra, and some other things where you can get it to draw the triangles and so forth, which, if you need a visual. Or ask Mrs. Ridgel, if you're in art class with her. She can probably draw that a lot better than I can.
She might kill me if I show her this.
And just show her the two curves. Say, can you draw three-dimensionally a triangle, right triangle?
Yeah, I guess if I didn't tell her it was
But it was back. Don't tell her it was back. Say, hey, listen, I got this picture. And off of this edge, could you show geometrically 3D how that would look? And then after you do one, can you do a couple more a little bit farther away from it and stuff. So, see if she'll bite and stuff. Because, I did that. I didn't do that with Coach Harris, but Coach Harris, I was talking about like the normal curve and then statistics. And so a couple years ago, his one of his classes earlier in the day, they actually did a 3D image printing thing of the normal curve for me, so I can use it as a template, and so I could draw a nice one in my class. So, I just asked, and he said, "Hey, we can do that for you," and they gave me 2 versions of it and stuff, which was sweet. Now, semicircle, we have 1/2. Remember, half of a circle is a semicircle. Semicircle is half a circle, so 1/2 pi r squared dx. Now, here's where the challenge comes into play. And again, I don't have a great picture going here, but if we just, if I think about, what kind of shape do I want to draw? If I draw our two curves from yesterday, and I have change colors. I don't want that. If I draw my line, and then I have my curve going like that. Okay, so I got my curve coming up above out of the iPad, going back down to the iPad, and I have this line that connects the two curves straight up. Okay, technically of a circle, what is that line? The diameter. Okay. So that's what we got to be careful here. So it's not just 1/2 pi r squared, because the r, the rate, we know that's the formula for the semicircle, but right now in the picture, that's actually the diameter. So when I go to set up this inside part actually, when we think about what is r, okay, and I know I write mine with capital R's, but our r is technically right now, it's listed as the diameter. So I need to do 1/2 times the first equation minus the second equation. So I need to take half of the distance between the two equations, and that actually gives me my radius. Okay? And so another way you could rewrite that, which might make it easier for simplifying purposes, is f of x minus g of x over 2. And that may be easier to use that format for what the r is, for this formula. Okay, so again, if you want a cleaner version of the whole thing at one stage, we can say the integral from a to b of 1/2 pi times f of x minus g of x over 2 quantity squared and then dx. So if you want a one-shot formula that will work, then it's the purple one. Okay? Again, the 1/2 is just part of the overall circle. It doesn't count for having the halving the radius or the diameter to get to the radius. Okay, so that first 1/2 is because I'm a half of the circle. Okay, so the other 1/2 is inside, because we got to take the f of x minus g of x, which is the diameter, and we got to divide it by 2, and that gives me my true radius. Okay, so again, if you're looking for a formula to memorize, to use with semicircles, the purple one is probably the fastest way to do it if you want to memorize a formula. Okay. All right, equilateral triangle says find the volume of each solid with the given cross sections perpendicular to the x-axis. Great. So then you're looking at it and you're like, oh, they want us to use this one up here. They want us to use our problem from yesterday. Okay. So with that in mind, I'm going to pull back over here. Y is equal to x squared. Y is equal to the square root of x. I'm going to pull back those two equations from yesterday's thing. Again, that was at the very top of the page. We know our integral was from 0 to 1. And then now I got to do, okay, what's the formula for volume of a equilateral triangle? It is the square root of 3 over 4 times my side length squared dx. So I've just got this generic thing set up first. The next thing I'm going to do is I'm going to fill in my side length. So the square root of which was on top, square root of x was on top. So this is technically my f of x. That was my g of x. So is the integral from 0 to 1 of the square root of 3 over 4 times the quantity square root of x minus x squared, that squared dx. Now, this is where I would go with the calculator. All right. If you're forced to do it by hand, you're going to have to FOIL out that square root of x minus x squared. You're going to have to FOIL that sucker out and then go through doing it the other way. So this one, we can use the Math 9 to our advantage. Again, you can pull, if you want the square root of 3 over 4 out front, if you want to do that, just make sure that you multiply your final answer by the square root of 3 over 4 if you do pull it out front. So as I get into my graphing calculator, I think it'd be easier if we go in there and type in my two equations. So square root of x for y1. For y2, I'm going to say x squared. And then now I'm going to go up there and go math number 9. And then, I'm in the graphing mode, sorry. Second quit. Math number 9 from 0 to 1 of, again, y1. So alpha ye, or trace that, minus alpha trace 2. And I need to put in some parentheses because I did not square that crud yet. So parentheses squared. And I'll probably need to go back over here and add the other parenthesis on the other side. Second insert parenthesis. Now that looks better. Got to make sure I square it properly, otherwise it'll give me the wrong thing. And then hit with respect to x and hit enter. And then I need to multiply that by the fraction, alpha y equals square root of 3 over 2. And whopping final answer should be, did anybody else get this? 0.113, 1113. Anybody else get that? Or are you banking on Mr. Stevens doing it right?
You did it over 2 instead of 4.
Oh, my creepy, my cruddy fingers. Daggone it. Oh, stinkers. All right, so hold on a second. We got to go back here. Thank you. So yes, you did not do it right. I did not do it right. So then I have to multiply that thing again by alpha y equals second square root of 3 over 4. 0.056. Is that better? Yeah, sweet. All right, so isosceles right triangles. All right, sweet. All right, so with that in mind, the integral from 0 to 1, it is 1/2 the side length squared dx. So the integral from 0 to 1 of 1/2 times square root of x minus x squared dx. All right. So now I'm just going to pull the 1/2 out front and type that in. So back to the calculator. And we're going to go math 9 from 0 to 1. I'm going to remember parentheses. Alpha trace y1 minus alpha trace y2. Close the parentheses, square it, and then dx. Okay. So I think I got that in there right. Hit enter. And then I got to divide it by 2. And I get, in this case, it is 0.064. So does the type of shape matter on what our volume is? Yeah, okay, it does. So that's why we got to be careful that we know which formula I'm supposed to be using. Because we know sometimes with certain problems we can do it multiple ways to get the same answer. But since I'm changing what geometrical shape is being the three-dimensional part of the volume part, it matters. Okay, so we got to make sure we're careful. So the last one, the semicircle, and then we get to call it a day for notes. So again, format-wise would be the integral from 0 to 1 of 1/2 pi times whatever my radius is squared dx. So that's integral from 0 to 1 of 1/2 pi times square root of x minus x squared over 2 quantity squared dx. I'm going to go ahead and pull out, because this is how we see mostly, this is how we see a lot of our multiple choice answers. We don't see them like this one. We actually see it to where they pull out front and it says pi over 8 times the integral from 0 to 1 of square root of x minus x squared dx. That's typically what we see most of the multiple choice answers as, where they bring the 1/2 pi out front, then they square the denominator. They square top and bottom, but then they bring out a 1/4 to multiply by the 1/2. So and again, typing that in right now the way I have it is a heck of a lot easier than typing in some of the other versions of it. So again, we can go back and say, give me a. I can actually go back and copy this answer, this equation. Yeah, I can use that equation, can't I? Or I can use that answer. And then I can say multiply it by the fraction pi, which is this button, over 8. And then I get that answer. So it looks like the semicircle one is pretty close to the equilateral triangle one in volume. I mean, really, they're all close together. It's just, so.